You think you understand gravity. It feels obvious, predictable, almost trivial. You step on a scale, a number appears. You drop an object, it falls. The moon circles Earth, the Earth circles the sun. Gravity is a force, a pull, a universal attraction acting across empty space. That story is so deeply embedded in our minds that we rarely pause to examine it. But the moment you slow down and look carefully, cracks begin to appear. Stand still and feel your weight. What do you actually experience? You do not feel a pull. You feel pressure, the floor pushing upward against your feet, the chair pressing against your back, the ground resisting you. Gravity, the supposed downward pull, is never directly felt. That is not a poetic observation. It is a physical one. If gravity were truly a force pulling you downward, your body would register that pull. But your nervous system detects only contact forces, the upward resistance of matter, preventing motion. That alone should make you curious. Now consider orbital motion. The moon is falling toward Earth right now. It has been falling for billions of years, yet it never crashes. It continues to circle. Newton explained this with astonishing brilliance. He proposed that every object attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. One equation unified heaven and earth. The falling apple and the orbiting moon were governed by the same principle. This was revolutionary. Before Newton, the heavens were mysterious and sacred. After Newton, they were mechanical. The universe became a machine. But Newton's theory, powerful as it was, contained philosophical discomfort. Gravity acts across empty space, no rope, no contact, no medium. Instantly. If the sun were to shift, Earth would feel it immediately. No delay. Newton himself admitted he did not understand how such action could occur without mediation. He called it action at a distance and confessed that the mechanism was unknown. The mathematics worked, but the explanation was incomplete. For 2 centuries, no one seriously challenged it because it predicted reality so accurately. Ocean tides, planetary motion, comets returning after decades. Even the discovery of Neptune came from slight deviations in Uranus's orbit, deviations predicted by Newtonian gravity. It seemed flawless, until a subtle detail refused to disappear. Drop a hammer and a feather in a vacuum. They fall together. Exactly together. This is not obvious. According to Newton's framework, gravitational mass determines how strongly something feels gravity. Inertial mass determines how much it resists acceleration. These are conceptually different properties. And yet, for every object ever tested, gravitational mass equals inertial mass, perfectly, to extraordinary precision. Why should 2 unrelated properties of matter be identical? Newton had no explanation. He accepted it as fact because it worked. But physics does not accept unexplained perfection lightly. This was not a small technical curiosity. It was a crack in the foundation, and it hinted that gravity might not be a force at all. Because if gravity were just another force, like magnetism or electromagnetism, there would be no reason for gravitational mass and inertial mass to be identical. Something deeper was hiding beneath the surface. And the next revolution would not come from better measurement. It would come from a change in perspective. Einstein did not begin by asking how gravity works. He began by asking what gravity is, and that question would dissolve the concept of force entirely. Einstein did not try to fix Newton's equations. He questioned the stage on which those equations operated. Until Einstein, space and time were assumed to be absolute. Space was a passive arena, flat, rigid, unchanging. Time flowed uniformly everywhere, independent of matter or motion. Gravity acted within this fixed background. But what if the background itself was not fixed? The first crack appeared in a simple thought experiment. Imagine you are inside a sealed elevator. No windows, No external clues. You feel weight pressing you against the floor. Are you standing on Earth, or are you in deep space inside a rocket accelerating upward? You cannot tell. Drop an object. It falls to the floor in both cases. Stand on a scale. It reads the same. Throw something horizontally. It curves downward in both environments. There is no internal experiment that distinguishes gravity from acceleration. This is the equivalence principle. And it is devastating. If gravity and acceleration are indistinguishable, then perhaps gravity is not a force in the traditional sense. Perhaps it is a manifestation of acceleration, but acceleration relative to what? Einstein's insight was radical. What we call gravity is not a force acting in space. It is the curvature of space-time itself. Space and time are not separate entities. They form a four-dimensional structure, space-time, in which events occur. Mass and energy do not merely exist within space-time. They shape it. Mass tells space-time how to curve. Curved space-time tells matter how to move. This is not metaphor, it is geometry. In flat space, the shortest path between 2 points is a straight line. In curved space, the straightest possible path, called a geodesic, may appear curved to an observer. The moon orbits Earth not because it is pulled inward by a force, but because it is following the straightest possible path in curved space-time around Earth. The apple falls not because something drags it downward, but because the geometry near Earth directs its natural motion toward the planet's center. You standing on the ground are not at rest. You are being prevented from following your natural geodesic. The ground pushes upward, accelerating you away from your natural trajectory. That upward push is what you interpret as weight. Weight is resistance to free fall. Free fall itself is not caused by a force. It is the absence of resistance. This explains why astronauts orbiting Earth feel weightless. They are not outside gravity. The gravitational field at their altitude is still about 90% as strong as at the surface. They feel weightless because they are in free fall. Their spacecraft and their bodies follow the same geodesic. There is no push, no resistance, no sensation of force. They are moving naturally through curved space-time. Einstein's theory predicted phenomena Newton's could not explain. One was the precession of Mercury's orbit, a tiny deviation that accumulated over time. Newton's equations fell slightly short. Einstein's matched the observation precisely. Another was the bending of light. If space-time curves near massive objects, then light, which follows geodesics, must bend as well. During the 1919 solar eclipse, astronomers observed starlight bending around the sun exactly as Einstein predicted. The geometry of space-time was not philosophical speculation. It was measurable reality. Time itself was no longer absolute. Clocks tick more slowly near massive objects. This gravitational time dilation has been experimentally verified countless times. Global Positioning System satellites must correct for both special and general relativistic effects. Without those corrections, navigation systems would accumulate errors of kilometers within a single day. Relativity is not abstract theory. It is operational reality. The universe is not a rigid stage. It is dynamic geometry. Mass and energy continuously reshape space-time, and everything, planets, light, galaxies, follows that curvature. Newton described gravity as attraction across emptiness. Einstein revealed that emptiness is not empty. It is structured, flexible, responsive. Gravity is not something that objects do to one another. It is the shape of the arena in which they move. And once that is understood, the universe transforms. Once gravity is understood as geometry, the most extreme objects in the universe cease to be mysterious anomalies. They become inevitable consequences. Consider a massive star. For millions of years, nuclear fusion in its core generates outward pressure. That pressure balances the inward curvature of spacetime caused by the star's mass. There is equilibrium. But when the fuel is exhausted, the outward pressure collapses. Nothing counters the inward direction of spacetime's geometry. The star implodes. If its mass is moderate, it stabilizes as a neutron star, matter compressed so densely that atomic structure dissolves. Electrons merge with protons. What remains is a sphere of nuclear matter, with the mass of the Sun compressed into a city-sized radius. But if the mass is greater, even neutron pressure cannot resist the inward curvature. Spacetime bends so steeply that every possible geodesic, every natural path, leads toward the center. There is no outward direction left. This is a black hole, not a cosmic vacuum cleaner, not an object exerting a pulling force, but a region where space-time curvature becomes so extreme that escape is geometrically impossible. The event horizon marks the boundary beyond which all paths point inward. Even light, which follows the straightest possible trajectories, cannot escape, because straight itself now leads inward. This is what it means for gravity to be geometry, and the consequences extend beyond individual stars. When massive objects accelerate, such as two black holes orbiting each other, they disturb space-time itself. Those disturbances propagate outward as ripples, gravitational waves. These waves stretch and compress space as they pass. In 2015, detectors measured distortions smaller than a proton's diameter, confirming that spacetime is not static, but dynamic and elastic. The fabric of the universe vibrates. Galaxies themselves form within vast gravitational wells, shaped by visible matter and something more elusive, dark matter. Though invisible, its presence is inferred from the curvature it produces. The large-scale structure of the universe resembles a cosmic web, filaments and voids shaped by gravitational geometry over billions of years. Gravity is not merely local, it sculpts the cosmos. Even time participates. Near massive objects, time flows differently. Clocks closer to a gravitational source tick more slowly than clocks far away. This has been confirmed with atomic clocks separated by mere centimeters in altitude. Time is not universal. It is curved. The closer you approach extreme curvature, the more dramatic the effects. Near a black hole, time dilation becomes profound. To a distant observer, objects approaching the event horizon appear to slow indefinitely. Space-time itself stretches. Under Newton's framework, gravity was an interaction. Under Einstein's framework, gravity is the architecture of reality. Mass does not pull matter through space. Mass reshapes space and time, and matter moves accordingly. This perspective dissolves the idea of force. What we once imagined as invisible threads connecting objects is replaced by curvature, a deeper, more fundamental structure. And yet, Newton was not wrong. His equations remain extraordinarily effective in regimes where curvature is mild and velocities are small compared to the speed of light. Einstein did not overthrow Newton. He revealed what Newton's equations approximate. Just as straight lines drawn on a globe appear straight over short distances, but reveal curvature at larger scales, Newton's gravity works locally, but yields to geometry globally. The deeper question is philosophical. If gravity is geometry, then the universe is not built from isolated objects interacting across emptiness. It is a unified fabric. Every mass influences the structure of space-time. Every motion is guided by that structure. We do not move through a void. We move within a dynamic geometry continuously shaped by matter and energy. Return once more to something simple. Stand still. Feel your weight. You are not being pulled downward. You are being prevented from following your natural path through curved space-time. The ground resists your motion along a geodesic. Your sensation of weight is the sensation of deviation from your natural motion. When you drop an object and watch it fall, you are not witnessing a force dragging it. You are observing matter finally allowed to follow the geometry of the universe. Gravity is not a force acting across space. It is the curvature of space and time themselves. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. This is not merely a correction of Newton. It is a transformation in how we understand reality. The universe is not held together by pulls. It is shaped by curvature, and we are participants in that geometry, constantly moving through it, guided not by invisible strings, but by the structure of spacetime itself. Once that becomes clear, gravity stops being obvious. It becomes profound. And the universe, once mechanical and rigid, becomes something far more elegant. A fabric, a geometry, a dynamic structure that binds apples, moons, stars, and galaxies into a single coherent whole. That is gravity, not a force, but the shape of reality.